3. This is video number 1 for the E1094-6 fourth quadrant DC motor field supply. Here's the connection diagram, and basically what we're going to do is we're going to run a quick set of signals so that we can take a look at the input, take a look at the output, take a look at typical test points within the 4100 firing board, and I'll show you basically what a good working unit should behave like. Here's the unit. It's being powered with a 240 coming from the utility, and then we have a step-up center top transformer where we have between L1 and CT 240 volts, and between CT and L2 240 volts for this particular setup. We have our two sets of anti-parallel SCRs that, along with the CT, will fire in one direction, or with the command of the polarity signal will fire in the other direction. We have the current feedback, we have the CTs, we have the span and bias on our board, and we have the polarity transition inhibit and field loss board. We also pick up here the board, and I think on this particular case we might be connecting independently, but what it's supposed to happen is we're supposed to bring in the 600 volts into terminals blocks 1 and 2 so that we get 120 on the secondary on the transformer that it's mounted on the unit, and it will show on the other side so that the board picks up the 120 and then further steps it down into 240. Here's the unit. So here's again our input going into the input terminal block, and then here we're picking up our output, and our output basically for illustration purposes is going to be a resistor. Here we have the DC output. We already have power. At this moment the board is inhibited, and the other thing we're going to do here is we're going to take a look, as we can see here, at a couple of test points on the board. We have test point 7, which is our zero cross, and we have our TP6, which is the delay angle. And although we have here a oscilloscope probe, we'll show in a second video how to measure the delay angle with respect to the 12 volts, so that the linearity of the duty cycle of this signal with respect to the 0 to 10 command can be verified. Alright, Tony, go ahead and enable, please. So you can enable by probably opening connection 7 and 8. Alright. At this point, what is your hi, Tony, what is your command?
Half a volt.
Half a volt?
Yeah.
We see we have now, but there's a reference. This is a 50% duty cycle, 60 hertz, and this is our delay angle. You want to go ahead and start increasing it, Tony, so that we can see a change on that particular signal. I see that we're having a problem, sir, with some grounding, but that's okay. We can see the duty cycle has now changed, and we can also see that. Go ahead, Tony. There we have our output, and this particular line coincides with the delay angle. And go ahead and bring it all the way down. And at some point, when the signal goes about below half a volt, it extinguishes. Alright, go ahead and bring it back again, 20 to 10 volts, please. So there again, the maximum output would be 90% of 240. So 90% of 240, it's approximately 213 volts. That's what it's showing right now. This is, we can see a full semi-sinusoidal wave being the output. Go ahead and you want to push the polarity, Tony, and we can see that the board inhibits, and it basically gets the same output on the different direction. Do you want to control the 0 to 10? All right. Alright, go ahead and bring it down until at some point it's less than half a volt, and it basically extinguishes. Unless we want to show anything else, this is the video number 1, which again shows the direct control of the 0 to 10 voltage for the delay angle and eventually on the output.